power of 6. Okay, 1 times 10 to the power of 6. So this will be equal to 2560 power of 3 divided by 3 plus by 1 power of 6. So this will be equal to 1.853 times 10 to the power of 6 millimeter to the power of 4, or 1.8533 times 10 to the power minus 6 meter 4. Again, what you see down here, the sequence are the same. Okay, so this number will drop to here. This number will just drop to here, mindless. If you arrange your data, so you can create like what I do. I create a spreadsheet to how to calculate second moment of area now. This simple geometry. Okay, so this you calculate where this comes to here, and finally this comes to here. Simple stuff. Okay, you will never make a mistake if you arrange your what data that way. If you arrange your data otherwise, okay, right. So I'm just showing you guys best practice. Okay, it's up to you going to use it or not. If you look at the solution manual, they don't have tricks like this for you. Okay. So you now find IZZ. Right, we're going to find IZZ. So IZZ1, okay, plus by IZZ2, and then plus by IZZ3. So IZZ1 is equal to 2.1067 times 10 to the power 6 millimeter 4, and then plus by IZZ2 and IZZ. So IZZ2 and IZZ3 is equal. So this is 2 multiplied by 1.8533 times 10 to the power minus 6. I forgot the minus 6 on the first one. I don't know why I put okay. So this will be equal to 1.8533 power minus 6 times 2 plus by 2.1067 power minus 6. So it's equal to 5.8133 times 10 to the power minus 6 meter 4. Okay. So what we just achieved is we have done, right? We have done, if you look at our formula, right? We have found our Vy, we have found our IZZ. Next, we're going to find our QZ. As I said, right? So we have done this. We have done this. Okay. So next, we are going to find first moment of area. And then we are going to look at the shear stress distribution equation. Okay. So we are going to do these two together. We're going to do these two. And these two, it's not really hard. Okay. If you obey the rules. Okay. It's not really hard. Okay. Any questions so far? Anyone?
Nope.
Nope. Okay. So I'm going to copy this diagram again. Someone is sharing his screen, you know. I don't know how this is going to work for me now. I have to. Unbelievable. Now can you see my screen now? Yes or no?
Yeah.
Yes.
Yeah, someone decided to share screen. Hey, don't be bored, okay? Get away from the control, you cheeky sort. Now I have to check whether is it still recording. Unbelievable. Okay, it's still recording.
It is.
Hello?
Yes, still recording.
Okay, still recording, okay. So now, let me... Lucky I checked. Someone is sharing their screen. Or not, we'll be recording his screen. And we will know who. Okay, so this is our, again, our structure, I'm going to copy. I'm going to paste in other places because I'm going to use this figure very intensively. So when your shear force is acting in this direction, okay, the horizontal part is always known as the flange. Okay. The vertical part is always known as the what? It's the web. Again, it depends on the direction of your what? It always depends on your direction of your shear force. Okay. So the first thing we're going to do is we are going to find, okay, I'm going to set a limit, okay? We're going to look at the flange section. Okay, we are just going to focus on the flange section for now, okay? So on the flange section, and we know that our centroid is over here, right? Our centroid is over here. So centroid from here to here, we found out that is 35 millimeters, right? That we know already. We are aware of it. That is 35 millimeters. So on the flange section, right, we're going to set our limits, okay? So the limits will be equal to 0.015 y, and it's going to go up to 0.035 meters. Now, some of you ask me, Eugene, why 0.015? So if we look at from our datum, so our datum is on our y-axis. So from the distance from here to here is what? It's equal to what? 0.015. You agree? Right? So this is equal to 0.015. And then to the outermost, this is equal to what? 0.035. Now, what rule did we apply? Right? We know our centroid, this is the centroid from our datum, but all of a sudden the arrow flipped opposite. So which rule did we apply? So if we go back to our rules, what did we say? Right? The datum of analysis is at the what? At the centroid. Okay, not at the datum that you pick, but it's from the what? Centroid. Rule number 2. Okay, we are applying rule number 2 now. So from here, I'm going to draw a bigger diagram so you can see better now. Okay, because there's a lot of okay. So this is only the flange section. I'm only drawing the flange section, right? And then so the flange section is 20. Okay, so this is where our centroid is. Right? So this is our ZZ. So what we have decided to do is we're going to form an equation of the first moment of area. Okay, we're going to form an equation. So we are going to stop the y variable over here. Okay, we're going to stop the y variable. So over here, this is our y. Right? And this is the area that we're interested in now. For now. And then we know that this will be our y bar. So somewhere in between. Not somewhere exactly in the center. Okay. This is going to be our y bar. Okay. So we are just focusing on the what? On the flange section. Okay. So QZ, so we know that the first moment of area will be in the Z direction, right? And then the QZ, so this is a QZ at the flange. Okay, where the limits is 0.015 to 0.035. So the area multiplied by y bar. Okay, now y is our variable. Okay, so if you look at the formula, right, when we derive this formula, the width is equal to what? The area. So the area. So I'm going to write the formula is the width multiplied by depth multiplied by y bar. Okay, so the width is equal to 0.16. The depth is equal to what? 0.035 minus by y, right? I'm going to move this. Okay, so this is b, and then we're going to multiply, or we're going to put a dot y bar. So our y bar dot y bar is equal to what? 0.5 multiplied by 0.035 plus by what? Y. Okay. So does this look familiar now? Yes or no? Remember we are deriving this, right? Where we are deriving this, our first moment of area. So when we are deriving this, what do we say? The area is C minus Y. The first, the Y bar is C plus Y multiplied by what? Half. Exactly what we have done down here. The C for this case is equal to what? 0.035 minus Y, then so on and so forth. Any questions so far? We okay? Right. So this will be equal to 0.08 multiplied by 0.035. Okay, 0.035 squared. Hey, I need more lines. Oh no, it's not clear. So 0.08 multiplied by 0.035 squared minus by y squared. Okay, so this will be equal to 98 times 10 to the power minus 6, and then minus 0.08 y squared. So this is our equation number 1. Okay, so we found equation number 1. Right. So from here, we can already calculate our shear stress. Yes or no? Okay. So the next thing we are going to do, we're going to calculate our shear stress. Okay. Of the flange. So what we have down here is going to be a distribution. So the formula is equal to Vy divided by Izz multiplied by Qz flange, and then divide by thickness of the what? Flange. Remember I told you the thickness is a what? The thickness is a variable, okay? So the thickness of the flange, comma, thickness of the flange will be equal. So you look at the direction of the shear force. Thickness of the flange is perpendicular to the shear force direction, so it's equal to 0.16 meters. Okay. So from here, your Vy, we calculate your Vy is equal to 90 times 10 to the power 3. Your Izz is equal to 5.8. 5.8133 times 10 to the power minus 6. Right. And then we have 98 times 10 to the power minus 6 minus by 0.08 y squared. Right. And then the thickness over here is equal to 0.16. Okay. So this will come out to be, right, so when you add everything up, this will come out to be 9.483 26 times 10 to the power 6 minus by 7.7409 times 10 to the power 9 y squared. Okay, so this is your first answer on the shear stress distribution.